Hey everybody, this is Erin from AaronsAudioCorner.com, and today I'm going to review the Buchardt S400 bookshelf speaker. If you're watching this review, you probably already know a great deal about this speaker, namely because so many other people have reviewed this speaker. But what I'm going to do is something a little bit different. I'm going to delve into more of the objective characteristics and relate that to what I hear when I listen to them. When you first see this speaker, one of the things you probably key in on is the large waveguide down here. Now at the center of this waveguide is a 19mm dome tweeter, and above it is a 6-inch woofer that is made by SB Acoustics. Now you may also recognize this woofer from the Revell line of Harman products. If I flip this around to the back, you can see a 5x8-inch passive radiator. Now what a passive radiator does is it displaces air as the frequency of the woofer itself begins to roll off. Kind of like a traditional vented enclosure, but without the actual vent. So everything here is sealed, so sealed in fact that as I press in on the woofer, you can see the passive radiator is moving. One other thing I'd like to mention is that you can see here that this speaker does also come with the option for magnetic grills, and they just go in and they place over the woofer or the tweeter, and it's really quite simple. But according to my data and my ears, you do not want to listen to these with the grills on. I would only put them on there for cosmetic purposes if you just want to keep people from touching it. But when you're actually, critically listening, make sure you take the grills off. Aesthetically speaking, this is at least to me, a very beautiful speaker. The white contrast with the black just makes this sucker pop. And I know that they have a black on black version, and I think they have a wood grain color version as well. But personally speaking, I really like this setup. Now I do also need to mention that Buchardt offers a 45-day in-home trial. This speaker runs about 1,800 euro, which it currently today is about 1950 USD. But Buchardt offers that 45-day in-home trial. So if you want to order them and listen to them and play them for a month or so, you've got plenty of time to do that. Experiment with placement in your room, move things around, see how you like them tonally. And if you don't like them, you ship them back. I think they make you pay about 25 bucks for return shipping. But basically, for $25, you can be loaned these speakers and try them out in your home. I highly suggest that you do that. Personally, I really like these speakers. There were some things about the frequency response that I didn't necessarily care for. Number one is there was a dip in about the 2 to 3 kHz region at the crossover point, which stood out to me when I was listening. I also noticed that there was a little bit of brightness in the 6 to 8 kilohertz region. Nothing terrible. To my ears, it seemed like maybe 1 or 2 dB hot, but enough for me to kind of catch it. This speaker does a great job of dispersing sound throughout a wide area, and that's really due largely in part to the implementation of this waveguide. Now, this dome tweeter is relatively small when you're talking about pairing a tweeter to a 6-inch woofer. And I say that because most 6-inch woofers, you would want to pair them with a good large 1-inch tweeter. This tweeter is closer to about 3/4 inch, 19mm, in that range. And the reason for that is because a 6-inch woofer will begin to beam somewhere in the 2 kilohertz region. I don't have a calculator on hand, but it's somewhere in that region. And when I say beam, what I mean is at the low frequencies relative to the diameter of a speaker, sound plays omnidirectionally. So it plays from all regions of a speaker. So picture that I'm just drawing a big old sphere around a single speaker. As you get higher in frequency, that sphere starts to collapse and aim forward. And basically we call that beaming because it's shooting a beam of sound more forward than it is anywhere else. So what you have to do in crossover design and speaker design in general is you want to make sure that as your speaker starts to beam and you bring in another speaker, that you match up their radiation patterns. And what I mean there is, let's say that this woofer starts to beam and no longer is it spraying energy at 360 degrees horizontally and vertically and orthogonally. It is, let's say that, for example, it's now beaming and it's playing most of its energy from 90 degrees off to the side and forward. So 180 degrees now instead of 360 degrees. When you bring in this tweeter, because it's very, very low in frequency, it will also play 360 degrees. The problem there is you've got a tweeter that's playing 360 degrees, you've got a woofer that's playing 180 degrees. you've got a mismatch in directivity. So one's playing sound everywhere, the other one's playing sound more forward. To help remedy that, usually what you'll try to do is you'll cross a tweeter a little bit lower before the woofer starts to beam, and that way the dispersion patterns are close to the same. So instead of the woofer having a 180-degree dispersion pattern side to side, so basically not plus or minus 90 and forward, now it's going to say it's closer to 360 degrees, and that tweeter now is playing 360 degrees. The problem with that is, in order to get that kind of interaction, most of the time you would have to cross a tweeter lower than it really needs to be played. So the benefit here is if they use the waveguide, that boosts that lowest frequency that it's playing a little bit more than it would be if it were playing on a flat baffle. So it increases energy in the low frequency area. And again, these are kind of relative terms. But it increases that energy in the low frequency area, and it provides them the ability to cross it to where you're not going to have to worry about damaging the speaker or creating a lot of distortion. So again, this is speaking in large generalities, but for those who aren't aware of how the directivity of a speaker works, that's a good starting off point. And if you want to look into that a little bit more, feel free to ask me questions in the comments section, or you can just Google speaker directivity, speaker beaming, things like that, and you'll find probably better discussion than what I can give right now in this brief intro. Going back to the dispersion of the waveguide, this waveguide allows this speaker to play within a range of about plus or minus 50 degrees. And what I mean by that is, if you're staring directly at the speaker, you're on axis, so you're at 0 degrees to the speaker. But as you move to the side, you're becoming more and more off axis. So at this case, I'm probably about 45 degrees or so from the camera right now. The problem with that is the energy that is dispersed from a speaker trends downward as you go further off axis. A good, well-controlled directivity speaker such as this one will keep that same energy even off axis, at least up to, plus or minus 50 degrees. Some of them, big horns, things like that, can control dispersion at higher angles. The reason that's important to have is because essentially what you're going to get there is you're going to get the same kind of sound radiated directly toward you as it is off the side walls, which all culminate together, and it's just more reinforcement, which is a good thing. Now you're also going to have the ability to sit in different places up front. So let's say that you've got a nice 2-channel stereo set up, but you want to share it with your friends, and you don't want to give up your sweet spot, but you also want them to kind of get an idea of what it sounds like. You can have them sit in one of the side seats, and they'll have a pretty good idea of what you're hearing, because the dispersion between 0 degrees on axis and their location at maybe 30 or 40 degrees off axis is still quite good and matches what you hear. That lightly touches on the frequency response, and I will get more into that when I go into the objective analysis. I also want to mention the impedance load that's on this speaker. This speaker has a nominal load of about 4 ohm. And for those of you who would want to buy this speaker and use it with like a standard AVR, like a Denon or a Pioneer, etc., you're probably not going to be able to do that. Most AVRs are only able to handle a load of about 8 ohms, sometimes 6 ohms. I actually ran this off of my AVR for a little while just to see if it could play and if it would, have any issues with my AVR. I think about an hour into listening to various music, my right channel on my AVR went out, and it was like, nah, I'm done, bro. I'm done. So keep that in mind. You're definitely going to need an amplifier that can handle a 4 ohm load for this speaker. So let me talk about a few things that I heard when I was listening to these speakers before I dive into the actual objective measurements. One of the tracks I listened to was Bruno Mars's 24 Karat Magic. I listened to that because that's got a lot of bass. It's got a lot of, it's a newer pop type song. So it's got a lot of things going on, and I pushed this speaker to about 93 dB at my listening position of about 11 feet. And then I started hearing the woofers unload. I'm not sure if it was the passive radiator or this front woofer itself unloading, but by unloading I mean you could mechanically hear pops. I was giving it too much power. Going down my list, let's see, the imaging was nice. The one thing I really liked about this, and again it's an attribute to the directivity control that this speaker has, is that I could move my head around in the seated area and the instrumentation placed on the soundstage didn't move. And that's a good thing to have, especially if you're a big fan of imaging. In order to get, at least in my experience, the imaging quality that you want, you need a few things. You need the speaker to have a matching frequency response with its sister speaker or brother speaker. And you also want the sound that's radiated forward to be the sound that's also radiated to the side and to the back, all those sounds that are coming toward you. Because if those all match and there's no smearing of frequencies, you don't have a null at 300 hertz coming at you from the side or from the side wall, while you have, not a boost, but just a flat line 300 hertz coming at you from the speaker, or the same thing for any other frequency in the bandwidth that a speaker is playing. Issues like that skew from reflection to direct sound, those cause image smearing as well. So that's something that you really don't have to worry about with this speaker, which is a good thing. Let's see. I did note again that the 6 to 7 kHz region was a little bit excessive. I said it needed about a little bit more, 2 to 3 kilohertz. Again, I believe after looking at the data that that's due to a crossover issue. And I really did like the kick drum on this. And I know one thing that I don't have in my notes right now, but in general, I think that I found the maximum SPL to be for general music, which would be, my 80s, my 70s, my 90s, and then my 00s and my 10s, pop music. It was about 95 dB was the max I could push this speaker at my listening position, which is actually pretty good when you consider that this speaker, is 7 inches wide and I don't know, at 14 inches or so tall. Somebody would have to look up the specs. I'm not going to break out my meter right now, but it's a relatively compact speaker. You can put this just about anywhere, and it gives you a lot of volume. Now, you definitely still would want to pair this with a subwoofer if you're going to be listening to, anything. I'm going to say like 95 dB and above if you're listening at maybe 12 feet. If you're listening closer, you're probably okay without a subwoofer. If you're a purist who doesn't want to run a subwoofer, you just want the raw speaker only. But in general, I don't think that there's any bookshelf in the world that wouldn't benefit from a proper subwoofer implemented into the system itself. So while I think this speaker is a great speaker and it does a good job of getting low, you're still going to want a subwoofer if you want to get some really high output volume. So I've tried to hit the highlights here. Again, this speaker has been reviewed to death by so many other people that I don't want to just recover their same traces, and I don't want to use all these crazy subjective words and all that stuff. That's not my style. So I'm going to flip it over to the objective portion, and we'll walk through the results that I've got from my measurements from Clipple Machine, and then some takeaways from my subjective as well, and how those tie in. I've gone to my website for the review. If you want to go here, this is where the data is. And I'm going to scroll down past the intro and past the pictures that I've taken and get to the data that matters the most. Let me zoom in first, make sure everybody can see this on their screens. This first image is of the impedance in the phase at 0.1 volt and 2.83 volts. The takeaway here is that the minimum load is 3.7 ohm. And that tells you that you're going to need an amplifier that will handle a 4 ohm load. Going down, this is the 2.83 volts impedance overlaid with the 2.83 volt frequency response value that's provided in this region. So if we're just looking at the on-axis response, you see that there are some nonlinearities in the 500 hertz region, and then the 800 hertz, about 1.6, 1.7K. There's a dip, and there's a little bump around the 7 to 8K region as well. And then this cancellation on axis is caused by the distance from the center of the dome tweeter to the waveguide. And that distance is about half an inch. So, and it does disappear as you go further off axis. It's not a huge deal, but something to take note of. Now, this is a graphic that I put more stock in, and this is what I feel like manufacturers should all provide. If they provide nothing else, they should at least give us this. This is the frequency response on axis. It is actually the same frequency response you see up here, but I have done a few things. Number one, I have taken the mean SPL from 300 hertz to 3000 hertz, and I've calculated it at 85.5 dB. I have also provided a gray window, which is the plus or minus 1.5 dB range relative to the mean, and then the blue window spans plus or minus 3 dB. This speaker does a pretty good job of staying within the 1.5 dB range, which is really quite good. Most speakers have have a tough time doing that. The good ones do it and do it well. There are some areas where it does go extend, or it does extend outside of that region. Again, the dip that I mentioned at around 600 hertz, and then the peak at about 1.7 hertz or kilohertz. And then again, this dip from the on-axis cancellation from the center of the dome tweeter to the waveguide. So all in all, it's not the best response, but it's pretty good overall. I don't know, and I cannot say for sure that if this speaker was voiced or not to provide this extra bump. I do know that this is more of a crossover concern, but my talks with Mads have led me to believe that they chose the best crossover point that they could arrive at, and also keep it within thermal limits so the tweeter would not break. So all in all, this is a response I think that was engineered essentially on purpose. I know that they could have done things differently to smooth out this directivity change through this region, which I'll discuss a little bit more. I should also mention that the F3 for this speaker is 53 hertz. The F10 is 38 hertz. F3 means that the response has fallen in level by 3 dB relative to my mean. That's how I'm calculating it. And then F10 is how the response has fallen in 10 dB relative to my mean. Again, that's how I am calculating it. This graphic shows you how the frequency response shifts as you move from in front of the speaker, which is on axis, to the side of the speaker at 90 degrees off axis. I also measured up to and beyond 90 degrees. I measured to the back side of the speaker, so 180 degrees, but I'm not showing all of those additional measurements in this graphic. Same thing for the vertical frequency response. I'm only showing you plus or minus 40 degrees. That would be where this information comes into play. This is the horizontal response, but laid out in a spectrogram type format. This shows the frequency hotness, I guess, for lack of better words, as you move from 0 degrees, which is the black line, to either side of the speaker, from 0 to 180 degrees or from 0 to minus 180 degrees. The point of this graphic, however, is more so to show you how does the radiation change as you move in frequency and you move in angle, forward or back, side to side of the speaker. What we're seeing here is, again, this 500 hertz concern that showed up earlier, and you can see that it's hot right around the plus or minus 50 degree window. And again, we're looking at those same resonances that we saw around 800 and around 1600 or 1700 hertz, and a couple more ripples. One other thing to take away too is the directivity. So the response is very, very wide up to about 500 hertz. That basically means that the woofer is playing omnidirectionally, and then there's this concern with the passive radiator interaction at the 500 hertz mark, and then you go up in frequency to about 1K and you narrow in directivity. And when you get to 1K, you go from, let's say this point is about 130 degrees, 130 degrees, and then all of a sudden you're jumping to about 90 degrees or so. You carry up, and then you get to 2K. And when you get to 2K, you're at about plus or minus 60 degrees, which is saying that the response is basically the same over a 60 degree window at 2 kilohertz. And then you move higher in frequency, and it roughly stays the same. I think at minimum, the response stays the same throughout plus or minus 50 degrees, which is really quite good. And one thing about that is that means that as long as you're sitting within that plus or minus 50 degree window of the speaker, you can toe them in, you can toe them out, you're going to have roughly the same spot or the same response in your seated position from that frequency on. So basically from plus or minus 50 degrees, the speaker should sound the same. However, when you put a speaker into a room, you have to deal with other things like floor bounce, side wall bounce, ceiling bounce, and then you've got room modes typically starting between 300 to 400 hertz in an average listening room. And that just means that your bass is going to start doing some crazy stuff, and that's not the speaker's fault. You can blame that on your room. This is the same thing that we discussed previously, except it's the vertical response window. This is a little bit different than I think most people are used to seeing. This is what I'm calling a global plot, a polar plot, whatever you want to call it. This shows you the same thing that the previous graphic showed you, except being squished down into a rectangle, I'm showing you over a 360-degree range. So you're still seeing the same hot peaks around 500 hertz, around 800, and around 1600 hertz again. But you're also seeing the plus or minus 50-degree window quite easily, where the response is pretty much the same throughout that region. And the one drawback, or the one caveat to that, I will say, is now it's more apparent that you have some higher frequency areas where the window response is a little bit more limited. So if you follow this darker line, which I'm not sure how well this is going to show up on a phone or TV, but it's darker toward the center, and as you move off the center to about 30 degrees, that darkness trends into more of the standard red. So this actually says that you're within about plus or minus 30 degrees. Still quite good. Normalized, and this is the vertical response. So I think I said to him about plus 10 degrees, minus 20 degrees or so, just depending on what frequencies you're looking at here. But overall, the listening window response is quite good. And that's what we're going to jump into next. So this graphic is the spinorama data. The black is the on-axis. The green is a listening window. The listening window is an average of measurements between 0, plus or minus 30 horizontal, and then plus or minus 10 vertically. Ideally, you want the listening window graphic to match the on-axis response measurement as well as it can, because then that means that within the listening window, it doesn't matter where you sit, your response is going to be essentially the same thing. You can see some deviation in some areas. Resonance, most likely these are going to be caused by the vertical axis and not so much the horizontal axis, but you can use some of the other graphics I presented to you earlier to verify that. Another thing I want to get to without taking too much time here is the predicted in-room response. This is a cyan, and I'm going to come back to that in a later note. Let's look at the early reflections directivity index. Now this graphic, this dash blue line, can be used to see how the speaker is transitioning from an omnidirectional polar pattern to a more directional polar pattern. Typically you see that when you transition from a woofer to a tweeter, where the woofer may be becoming more directional because it's playing outside of its beaming range, which is to say that as you increase frequency relative to the size of a speaker, the speaker no longer radiates omnidirectionally, it radiates more forward in one direction or more backward, but it no longer radiates out to the side, it radiates forward and back if it's a dipole type speaker, namely forward. So, following along, if you had a perfectly omnidirectional speaker, this blue line will be flat across 0. I've never seen that. I don't know that I ever will. That would be the ideal omnidirectional directivity index value. So we're going to follow this blue line up, and when it gets to about 500 hertz, you see a jump in directivity, which means no longer is it wide, it's become a little bit more directional. Now it's more wide again at 600. Now it's becoming more directional as you increase in frequency. And then when you get to the 1.2 or 1.3 kilohertz region up into about 2 kilohertz, there's a sharp jump in directivity, and then it dips back down. This is where your woofer is going to meet your tweeter at the crossover region. And once your tweeter has fully taken over, the directivity slowly increases, but it's actually very well controlled, especially from about 4K to about 13K or so, and you've got that on-axis dip at 16 kilohertz again. This is the early reflection curves breakout. You can read more about this when you have some time. Essentially, this just tells you where to put treatment in your room. You'll also notice that this rear wall bounce in red is significantly different than any of the other bounces. That's because this rear wall bounce is a predictor of reflections coming from the rear wall. You're not going to have a lot of high frequency reflection off the rear wall because the tweeter in this speaker is only facing forward. There's no rear facing tweeter here. This is the important thing that I want to discuss. This is the predicted in-room response. Now this predicted in-room response in black is a calculation based on various curves of how your response curve is going to behave in your room based on this speaker. And it's actually a really good predictor, which I'll get to again shortly. The target curve is an idealized curve that most people would like. Research has found that this is a favorable curve. It decreases at 1 dB per octave. And when I took that to my room, or took the speaker into my listening room and actually listened, This is the same thing as the graphic you just saw. The black is the predicted in-room response curve. The red is the target curve. The blue mic, or the blue curve, and the green curve are the actual measurements I got in my room. The blue one represents my listening position, and then the green represents the microphone being placed, or moving microphone average taken across all 3 seats of my front row of my home theater. And what you're seeing here is that the predicted in-room response curve above about 1K is almost exactly what I measured in my room. Below that, you're going to wonder, well, why is it kind of all over the place? Well, I got 2 things. Above or below about 300 hertz, mostly room modes. And between about 400 to 800 in my room, I have some home theater loudspeakers that are placed behind a false wall. The speakers that I'm listening to, in this case the Buchardt S400, were placed in front of those home theater speakers. So I've got some weird things going on because of the proximity of the listening speakers to my home theater speakers. So if those home theater speakers weren't there, this curve, or all these measurements, would line up better to the predicted in-room response curve. Now we're going to look at distortion. These are distortion measurements taken at various voltages, and I have calculated an average SPL. That average SPL is based off, I'm increasing the voltage this much. My average SPL at 2.83 volts is about 86 dB through 300 hertz to 3 kilohertz. So if I increase the voltage X amount, the output SPL should equal X amount in SPL. And that's just a straight calculation, assuming no losses. What you see here is the 500 hertz to 600 hertz region. There is a strong peak there. I'm thinking that's from the passive radiator, but I'll get to that in a second. There's a couple other ones down here, and then there's some higher distortion above about, what is that, 8K to 9K hertz region. And naturally on the lower end, you expect that as you pump a whole bunch of volume into a speaker that, without a crossover, the distortion is going to increase, especially in a smaller bookshelf like this speaker. And that's okay. Now I will say that I didn't hear any of this distortion, and I think this is because it's so high or so narrow in bandwidth that it wasn't completely audible to me. Don't believe that I ran into anything like this. I didn't mention anything in my notes. Maybe if I went back and listened again, I might be more receptive to it now that I know it's supposed to be there. But I did notice below about 80 hertz, I was having some mechanical issues at higher output volumes. I think above about 95 dB or so, I could actually hear the woofer start to be limited in excursion. I mean, I could hear it mechanically overexert itself, for a lack of better words. So now if I roll down to the compression amplitude measurement, this is if I'm pumping X amount of voltage into a speaker, I expect it to provide X amount of decibels output. And what I'm seeing here is on the lower end of the response, I've got some higher compression, but nothing that was terrible, nothing that I noticed in my listening, because I never pumped this speaker actually to this voltage here. The reason for that was because before I got to this voltage or SPL level, I could actually hear the woofer physically start to reach its maximum output. So I wasn't listening at levels like this, so I can't say that if anybody else was, that the compression would be audible. I think you're going to run into the mechanical issues before you even hear the compression issues. Grill on versus grill off. This just shows you to keep the grill off. You see a lot of comb filtering going on, so keep the grill off. This is step response for people who care about timing more than I do. This is a near field response. So the green is the woofer, red is the tweeter, blue is the passive radiator. You'll see in the 500 to 600 hertz region, well, actually extending even down to 400 to about 800. So this block, this seems to be an indication of passive radiator breaking up. And I think that's what was contributing to the 500 to 600 hertz region having some issues. It's either that or it's a pure acoustic thing as you're moving from side to side. To be honest with you, I don't know the reason. I didn't really hear it in the music that I listened to. Others might. But again, Buchardt has the listen at home for 45 days trial period. And I suggest that you give that a shot if this is something you're interested in. Now that we've been through the objective portion of the analysis, let's look at my subjective notes and try to correlate these back to the objective analysis.
One thing I noted was the lack of a high pass filter, because I wasn't using a high pass filter during my listening tests, limited the SPL that I was able to achieve. I believe I got about a maximum of 95 dB at 11 feet. So if you're about 5.5 feet, that's 101 dB. So that's still quite loud, especially out of a bookshelf speaker. The John Mellencamp track I said was wide, and I believe that has a lot to do with the radiation pattern of these speakers actually being about plus or minus 50 degrees. The female fundamental vocals were nice. Male vocals were a bit thin. That could be relative to the 80 hertz region. I might have to go back up and see, but I'll skip that one for right now. The image is locked in. That's because the directivity on this is relatively low. Again, the radiation pattern is pretty wide, so I can move around a good bit and have a good stable image wherever I went, up at least on the front row. I did have that the 6 to 7 kHz region was a bit too hot, and also maybe even the 8 kHz region. If you go back and look at the response, the frequency response, or any of the other axes of measurement, you can kind of get an understanding for why that is, especially when you compare it to the predicted in-room curve and the real measurement curve that I have in my room, how those two correlate so well. And then you overlay that against the negative 1 dB per octave, you can see that the 6 to 8 kHz region was about 2 dB hotter or higher in frequency or higher in output than that target curve suggests that I would have otherwise liked. 2 to 3 kHz region was lacking in presence. I will attribute that more to the directivity mismatch as the woofer transitions to the tweeter. The kick drum was nice in Rage Against the Machine, but I did hear some unloading of the passive radiator or the woofer. I'm not sure which exactly it was because I was far away from the drivers as I was listening. But I did hear that. That was a mechanical issue that I noted previously. And again, I'm saying a very wide sweet spot. So those are some of the subjective things that I heard, and they all actually correlate very, very well to the objective data. So those of you who say that objective data measurements don't matter, you're not looking at the right stuff, or somebody's not giving you the right measurements. That's going to cover it for my objective portion. There's a whole lot more data in here, a lot of other notes that I highly encourage you to go read if you have time. And if you have any questions about it, as always, please feel free to ask me. I wish I had more time to get deeper into some of this, but this video would be an hour long, and I'm thinking I'm already scaring people away as it is. So that's going to cover it for the objective. Let's switch back and look at my beautiful face again.
That's going to do it for this review of the Buchardt S400. I hope you learned something. I hope that the data taught you something new today, and I appreciate you following me. If you want to subscribe, go ahead and do that. And yeah, I think that's it. I appreciate all your help and your support. Peace.
Come with it now! Wow, wow, waka, wow, wow, waka, 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 wow, wow, waka, wow, wow, waka, waka, waka.